try to cover in this AP review is obviously not everything we covered in AP. It's going to be stuff we're going to have covered in Chem 1 that we didn't touch much in AP. All right, and sometimes we forget some of this easy stuff because we've been working on some of the hard stuff for so long. So let's talk about this. Do we remember how to do these kind of things? I'm going to start from the bottom up. Start with atomic structure. If I told you an atom has 11 protons and 14 neutrons, could you tell me all this other information about it? Do you remember how to do that? Some people are shaking their heads. Some are saying, yeah, this is easy. If it's got 11 protons and it's a neutral atom, how many electrons has it got? 11. Okay. What's the mass number mean?
It's protons.
Protons and neutrons added together, so that would be what? 25. Right? Now, do be careful. Is that mass number exactly the same as that number up in the periodic table? That's the atomic mass up there. That is the average atomic mass, which includes the averages of all the isotopes. This is for a specific isotope who has 11 protons and 14 neutrons. So I can write this two different ways, and I can write a hyphen notation or a nuclear symbol. And either way, I've got to know what element it is. How do I know what element it is? That tells me what element. That never changes. The protons never change. The protons are another name for the atomic number. Okay? And the atomic number never changes. Who is 11? It's sodium. So that will be Na. And then you put the mass number, 25, over the atomic number, 11. Got it? Okay? And that's what you would write for here. But you should be filling this in with me. All right? And then this, or you could write sodium 25. Okay? And that would tell you the same information. Okay. I can give you different information and you can find the same stuff. Watch. Here I gave you the number of electrons. Here I gave you protons and neutrons. If I know the electrons, I know also the protons. But this time I gave you the mass number. And if I know the mass number, how do I get the number of neutrons? Yeah, I'm just going to subtract. That'll give you 6. All right, I'm just making these numbers up. God knows if any of these actually exist. But I do know that an element with 14 protons exists. Who is it? Silicon, and that would be silicon 20 over 14, or Si. A lot of people do this for a simple mistake. Si 14. Is that correct? Yeah, you got to put the mass number after this, not the atomic number. A lot of people do that. And finally, if I just give you that, you can fill everything else in if you have a periodic table. And by the way, I made copies of the periodic table that you will be using on the AP exam. Those periodic tables are different from the ones you've been using for me. Mine have more significant figures. All right, theirs are more rounded. They round off a lot of these numbers for the atomic masses, mainly because they're not caring about specific, for most part, they're not caring, especially the multiple choice, specific calculated answers with significant figures. All right, they do. There are times you have to keep it everywhere you're supposed to, but I always kept more significant figures, and I gave you a periodic table that has more of them on it. I want you to get used to using that one. Anyway, you could certainly do that, guy. If you knew him, you knew oxygen, you know oxygen. Atomic number is 8. Here's a mistake, I guess I should mention to you. People see oxygen up there, 15.999, and so they think to themselves, okay, so the mass number is obviously 16. It is not. It tells you in this case, this is the isotope oxygen 17. All right? It is not oxygen 16. That number up there is an average of all the isotopes. It is not the specific isotope. All right, so you remember how to do those. And there's a lot of variations of the questions I could ask you. Now, next thing we didn't talk about at all this year, but we talked about a lot last year, were electrons. And we're going to start from the bottom here up. Starting from the bottom up for electrons, the quantum theory. Basically, I broke the quantum theory down into 3 statements. And I spent a lot of time on the third one, quantum numbers. The first one says electrons can only exist at certain energy levels. Think about this. All right? The weird part about this is they can also change energy levels. Why is that weird? Well, because how do they get there? They quantum leaped. I'm going to talk about that in the Bohr model of the atom in just a minute to remind you of all this stuff from Chem 1. But before I do, I wanted to point out something. I purposely put this up here. I want to point out something from Chem 1 that I gave you that the equation on your sheet is different. It's slightly different. Here's what I gave you. See this? Because that's the one I use more often. I just wanted you to use that. And I also gave you this equation, C equals wavelength times frequency. Now, the thing is, there's two problems with this. On your sheet you're going to get for the AP exam, it doesn't give you this equation. This equation isn't there. you can see, I'll bet you anybody who has any math skills can see why, if it gives me this equation and this equation, it doesn't have to give me that equation, right? Okay, so everybody can see that. But I don't want anybody to be confused by that. All right, that's the equation it gives you, and that's the equation it gives you to solve for frequency, wavelength, and energy changes, or energy. Now, second problem is, I used an F for frequency. Look what it uses. A lot of people will be confused by this. Okay, it uses like a script kind of V. All right, that's what it uses on the sheet. Okay, I don't want anybody to be confused by that. So let me get to the problems. I want to do a couple of problems with this on the second page you're on now. Okay, turn it over. All right, those are the two things it gives you on the formula sheet for the AP exam. Those are the exact two equations it gives you written as they write it, with a V instead of an F. If I gave you this question, which I am, how would you solve this? You say, well, I got to do some rearranging, or I have to do two separate problems. Okay, you could do either way. I could do this as two separate problems, or I could rearrange it. It wants an energy of a photon, so it wants the E of a photon. And we know E equals h times frequency. But there's a problem with that. It doesn't give me the frequency, it gives me the wavelength. What can I do if I want to do this as one equation? I could substitute in the formula for frequency. Frequency, this guy right here, can I get frequency from that? Sure. Frequency would be, you're going to divide both sides by wavelength, would be C over wavelength. So E would equal h C over lambda, which is exactly what I gave you when we had that in Chem 1. So you could do it like that, substituting into the equation, and then you will be given on the test Planck's constant, 6.63 times 10 to the negative 34th, I think it is, joule seconds. You are going to be given the speed of light, 3.00 times 10 to the 8th meters per second. And the wavelength is told to you to be 5.59 times 10 to the negative 7th meters. Okay? So that's how you would do that problem. And whatever you get for that, I'm not caring about. This is a review. I'm just trying to show you how you would do it. So write that all down, and that's how you would do that guy. Again, could you have done him by doing this equation first? By just using that equation first and solving for wavelength, and then solving for frequency, and then plugging frequency into this equation, doing it in 2 steps? Absolutely. Doesn't matter. Either way would be acceptable, but you would need to show the formula and the work so they know what you're doing and you're not just throwing numbers around like a lot of you guys are still doing after 2 years of me yelling at you about it on that last test. All right? But anyway, let's do another one. Okay? Look at this guy. Find the wavelength of light that has an energy of 3.5 times 10 to the negative 15 joules. I want wavelength. I'm given energy. You would know would you know what to do? Again, you kind of have to rearrange the equation and do the same thing. I'm not going to do that one here for you, but I do want to do this one because when we get our answer, I'm going to ask you what the units are, and we'll see if anybody remembers what they are from Chem 1. Let's do this guy. This is a real easy equation, right? It wants the frequency, and it gives you the wavelength. And there's your equation for frequency and wavelength, right? So C equals wavelength times frequency, right? Write this down. I want frequency, so I'm going to divide by wavelength, right? So I get frequency equals C over wavelength, which equals 3.00 times 10 to the 8th meters per second over the wavelength it tells you is 5.59 times 10. Now hold on a second, 10 to the negative 5th centimeters. Can you convert that to meters? Yeah. All right, if I were converting that to meters, centimeters on the bottom, meters on the top, 1 meter contains, I'm going to make him smaller by 2 spaces. How do I make a negative 5 smaller by 2 places? Negative what? 7, okay, meters. Now at least my meters will cancel. But it doesn't leave me with the units you're thinking. It does not leave me with the units of seconds. What does it leave me with the units of? Per seconds, 1 over seconds. Which is what? Hertz. Exactly. I don't care what that number comes out to be. You can do the math on your own if you want to. But hertz is 1 over seconds. And you have to remember what hertz really mean. Hertz are how many waves are going by per second, right? If you remember Bill Nye with the little kid on the stick and he was moving waves by him and he's counting 1, 2, 3. How many go by per second? That's what hertz are, okay? And that's what we measure frequency in. per seconds, okay, not seconds. All right, good enough. So there you go. That's a little review of that stuff. You will probably see something about wavelength, frequency, energy somewhere in there, and you'll have to know the relationship. You don't have to memorize it. These equations, those two equations are up there. As long as you can manipulate them, hopefully you can. All right. Sticking with the electrons. Remember this. Haven't done this all year long. Okay, can they ask you about these? Sure. This is not going to be given to you on the test. This is not. All right. Now, this is not a memorization thing, people. This is just being able to count from 1 to 7 and knowing how. Look, here's the way you remember this. Obviously, 1 to 7, that's not hard. But there's one energy, there's one shape in the first energy level, 2 in the second, 3 in the third, 4 in the fourth. Actually, theoretically, there might be 5 and 6 and 7 in those, but we don't know because we run out of electrons. Either way. This shows, once you do this, this tells you the order in which they fill. All right, so let's just do a couple of these guys. Let's do nitrogen. I'll start with nitrogen, and he'll look like this. First thing to fill up, 1s. I put one arrow, one blank underneath it. That represents the magnetic quantum number. Okay, and then the spin quantum numbers are the arrows going up or down. What would I write next? Anybody? 2s, okay. Why? Because 1s, then 2s, then 2p, then 3s, okay. All right, so 2s has 2 electrons in them as well. I've taken care of 4 of nitrogen has 7 electrons to take care of. Where do the next ones go? 2p, but the 2p is going to have 3 blanks underneath him. 3 positions in space. 3, that's the magnetic quantum number for him. And I only need 3 more, and they go in 1 at a time, which brings me to a rule. What rule is that? It tells me they go in 1 at a time. Do you remember it? It's called Hund's rule. All right, and that you do remember that it does that, though, right? It's called Hund's rule. Okay, so they go in 1 at a time. Now let's keep going from there. I don't want to have to rewrite it again. Vanadium has, where is he? 23 electrons. So I got to fit 23 electrons in for vanadium. All right, well, that would give me 6 more there. I've got 10 at this point. I got to keep going. What fills up after the 2p? After the 2p comes the 3s. That gives me 12. I got to get to 23. After the 3s comes the 3p. That gives me 18. Okay. After the 3p comes the 4s. That gives me 20. I need 3 more. Where are they going to go? Those electrons for vanadium are going to go after the 4s comes the 3d. 1, 2, 3, 4, 5. I only need 3 of them in there, and that's what he would look like. Again, Hund's rule comes into play. Let's talk about these guys. If I were to do electron dot notation for a guy like this, is it going to, how many electrons, how many dots are going to be in this guy? What's the highest energy level for vanadium? 4, not 3d. I don't include those. So the electron dot notation for vanadium is just going to look like that. Remember? Matter of fact, let's look at the next guy after vanadium, chromium. He would be that. What was chromium's electron dot notation look like? Same thing. We're only including the outer shell electrons. But those transition elements, these guys that have incomplete d sublevels, there's weird stuff that goes on about them. Okay? All right, so a lot of strange things happen here. Most of those guys in there have multiple charges. And they have them frequently, multiple oxidation numbers. Unlike fluorine, chlorine, oxygen, these guys, well, chlorine has different ones too, but fluorine and oxygen and hydrogen, they almost never change. And most of the other guys who are strong nonmetals and strong metals rarely, if ever, change. The guys in the middle, they have different oxidation numbers all the time. We know that. Iron, +2 and +3. Copper, +1 and +2. All right, many of these guys have multiple oxidation numbers. Can we use shorthand notation? Do you remember how to do that? Let's look at a guy like tin. Tin is over there. He's got 50 electrons. I don't want to write 50 arrows out. So I would take the nearest noble gas that came before him, krypton. Krypton takes care of my first 36 electrons. Okay? 36 electrons are taken care of by him. But I've got to know where to pick up from there. I got to know where to pick up from. I don't start with 1s, 2, and that's going to defeat the purpose. Where do you think I pick up? Well, there I have to go to, I don't know if it's on this next board or not. No, I'm going to have to skip ahead a little bit. I should have put one on here to show you. There I have to go to this. Okay? Remember this? This kind of tells you everything you need to know. I'm going to get to the periodic table and trends in a minute, but I probably should have had this slide up here beforehand. Take a look. This block here, all these guys, that's where the S sublevel fills. That's where the shape S fills. This is where the D shape fills. This is where the P shape fills. And this is where the F shape fills. Okay? So I can tell the last thing I'm going to write on any periodic table element just by where he's located. I can. All right? So the last thing I wrote for krypton, who was right here, I believe, 1, 2, 3, fourth one down, right? There was krypton. The last thing I would have written for krypton would have been 1, 2, 3, 4. Fourth energy level is the highest energy level. What block am I in? P. And he's the last one in that block, so how many electrons would he have? 6. So the last thing you wrote for krypton would be 4p6. Let's go back to that. Remember I told you what we were doing here. We were taking krypton as my, you have that written down already, with 36 electrons. So the last thing I wrote was 4p6. What fills after the 4p according to the diagonal rule? 5s. If you want to know where, if you don't even have a diagonal rule, can you figure that out anyway? Sure. What's the next electron? 5s is going to fill up right there. Fifth row down, that's the highest energy level, S block, 5s. That would take care of up to 40. Then I would have to fill after that. I could just look here. The 4d comes after that. 4d, 1, 2, 3, 4, 5. 10 electrons fit in there. That gives me a total so far of 50. Tin has, no, I'm sorry, not 50. 48. Tin has 50. So the next ones have to go where what fills after the 4D? The 5P. 5P would have 2 more in there, and that's what tin would have looked like if we were withdrawn. So you could do them by knowing the. You could do it by knowing the diagonal rule, or you could do it by knowing this. Okay, knowing what shapes fill, what's the highest energy level, pretty much what's the last thing you're going to write for any given element. You could do that. And I'm going to go over these in a little bit when I get back to that. But I got to get back to the sticking with electrons. All right, so we just did those electrons. Now, I also wanted to, because there's people who had me last year who saw this, but if you had me 2 years ago or if you had someone else, you probably didn't. Okay? So let me talk about this. This is the Bohr model of the atom. All right? You often hear them use that in some of my practice tests. They talk about this, all right, and what happens. The Bohr model was an early theory, and it breaks down after you get, it holds up pretty well for hydrogen, but it breaks down as the atoms get larger. And there are things that aren't correct about it. But there are also things that we all know happen to electrons, and this illustrates very well. Okay, so let's take a look at what happens when electrons change energy levels. First of all, Bohr theory says that electrons, one of the things it was wrong about is predicts these circular orbits, these, which are not correct. But it is true that there are certain energy levels they can only exist at, 1, 2, 3, 4, so on. And they can change energy levels. Let's watch what happens. When an electron absorbs a photon of energy, it jumps, it quantum leaps up to energy levels, but it doesn't do it like up there and then right back down. Sometimes it goes in stages. It goes up to a certain energy level, then down one, and then down another one. And because of that, you can actually see every time he moves, he gives off a specific amount of energy, which is related to the wavelength of light by the equation delta E equals hc over lambda. So the wavelength's related to the energy change. The larger the energy change, the smaller the wavelength, and vice versa. The smaller the energy change, the larger the wavelength. The thing is, something I never really talked about a whole lot and we didn't really use, you can actually see those colors. We did talk about this a little bit, but they're actually colors. Remember doing the flame test lab and the spectroscopes? So you looked through the spectroscopes and you saw things that look like this, okay, for specific elements. Actually, they looked a little bit more like these over here, right? Where you had to identify an element based on it. Okay, the reason that happens, the reason you get these specific lines, they correspond to specific energy changes by the electrons. And you can actually, hydrogen is really well mapped out. There's a series of lines that you get that fall in the visible spectrum for the most part. The Balmer series falls in the visible spectrum. So you see a red line, green line, a blue line, a purple line. All right, but there's other ways that these electrons can, that one electron of hydrogen can change its energy levels and get back to its ground state when it gets excited, depending on how much energy it receives and what energy level it jumps up to. We don't see all of them because some of them fall in the ultraviolet light, some of them fall in the IR spectrum, but we can see certain colors. So if I go back to this one, here's the thing. Look at these two spectrums so you understand the difference. This is what you would see. Look here. This is what you would see when the electron's falling back down. When it falls back down, it gives off that color. It gives off that. You saw the colors in flame tests. That was what you were doing in a flame test. You were exciting electrons. They jumped up to a higher energy level. When they fell back down, they gave off a color. But they don't give it off like my pen drops. They gave off a bang, a packet, going from here to here for the blue color, from here to that energy level to that energy level for the purple color, and this energy level for the red color. And so you can actually, that's why you can see this. Now, depending on your electrons you have in the atom, depending on what atom you have and how many electrons he has, that spectrum, which is the emission spectrum, is what it's giving off, will be different. Hydrogen's emission spectrum is completely different from helium's, completely different from sodium's. They all have their own unique, like fingerprint spectrum. By the way, this is the absorption spectrum. Notice the lines are missing because they've been absorbed by hydrogen. Okay, that's the absorption, that's the emission spectrum. We look mostly at emission spectrums that kind of, here's all the spectrum. Remember, the first thing we did when we had those spectroscopes is we looked at a light bulb, which gives off, an incandescent light bulb gives off all the colors of the rainbow. Or we looked out the window. You saw the full rainbow. But if you looked at, that's what you see, full rainbow from that. But if you look at strontium, you would only see the electrons that are changing energy levels. Or if you looked at barium, you would only see electrons that are changing energy levels. For hydrogen or helium, and that's what you saw. They're as different as fingerprints. Okay? All right, good enough. Now, sticking with and ending my talk about electrons and atoms. This is, we realize I'm doing about 3 chapters worth of material in about 15 minutes. You understand that. It's not stuff that I expect you to have to, like if I were teaching it, I wouldn't be doing it this fast. But we've seen this all before. I'm just reminding you it's on a test, and you should look this over before you get there. Say I gave you some guys like this. You can predict whether a guy, just from looking at his electron configuration, whether a guy wants to be a metal or a non-metal, whether he wants to lose or gain electrons, and how many he wants to lose or gain, based on its ionization energy. Would you expect, for example, let's take a look. Would I expect that I would get, be very difficult to remove that electron. Forget about everything else. Just look at everything else about this guy. He's got 1 electron in the 3s. And then he has an octet. Is it going to be hard to remove that 1 electron? No. It's going to be a very low energy level, whatever that number is. Okay? Low energy to remove that, I should say that. But to remove the next one, to remove the 2nd electron, there's going to be this huge jump. It might be like 1,000 kilojoules of energy. But it depends on what they use. Kilojoules, they use different units of energy. But you will see a big jump. Now, after that octet is broken, you would expect that it's not as bad, but it never goes down. This would not be less than, say that was 1,000. It would still be maybe 1,300. I'm just making up numbers. My point is, it never goes down, but you'd be looking for where this big jump. How many does he give up without any trouble? What would you, if I gave you those numbers up here, would you expect it would be easier or harder to remove this electron than that electron? Think. Harder, right? Why? Well, I'd say for a couple of reasons. One, that electron is paired up in the s sublevel. We know filled sublevels have extra stability, right? 2, as I go across the periodic table and I keep adding electrons and protons, I'm adding a proton and an electron each time, I'm increasing the charge. Remember what happens to the size of the atoms as you go across the periodic table? What happens to the size of those atoms as they go across? They get smaller because you're getting more and more positive charge and more negative electrons out there, pulling them closer together. That's called Coulomb's law. The stronger the charge, the closer together they are. All right, they're going to pull themselves closer together. So I would expect this guy to be maybe a little bit higher, maybe 138. I'll make up a number. But do you think it's going to be a big jump? Do you think this guy is going to be as high as this guy? No. To remove that 2nd electron out of there, all right, it might be, it might be 350 or something. It'll be more, but it won't be a ridiculous number. Where's the ridiculous number going to come after you remove those two and you want to break up that octet? You know what's going to happen. It's going to be, 1,800 or something like that. Some big, big number. All right? So that's basically how you can predict what charges these guys would have. What charge would you predict? How many electrons does sodium generally tend to lose? 1. How many does magnesium tend to lose? 2. Okay? And so aluminum, I bet you realize, probably give up those 3 before he breaks up an octet. 3. Okay, this is all going back. Now, you realize why we haven't talked about this for so long. This is the reason behind when I ask you, okay, what's the charge of calcium? You say +2. This is the reason behind it, because of the electron structure, all right, how many electrons they tend to lose or gain. Ionization energy being the energy required to remove an electron from an atom. Okay, and we use it to predict these ions charges. Now, there's something I did not cover in Chem 1, and I noticed is on the test, and I should mention this to you. Something is called para and diamagnetic. You have to kind of just memorize this, okay? Something's paramagnetic if it has one or more unpaired electrons, okay? So when I say unpaired electrons, let's take a look at these guys up here. If I have everybody in magnesium, for example, everybody in magnesium, for example, would he be paramagnetic? If I were to draw him out, do you have any unpaired electrons for magnesium? Well, let's think about it. The last thing, all of these are paired, right? P is like this. They're all paired up. S, 3s would end up like this. He's paired up with 3s too, right? So he would not be paramagnetic. All right, he would be diamagnetic. Dia, think of di as in 2. Everybody's paired. Dia, okay? And diamagnetic things like magnesium are not going to be attracted to a magnetic field. They're not going to be magnetic, okay? This is more of a physics concept, which is why I never really covered it. Did you guys cover any of this in E&M? You are people in E&M here, right? Did you guys talk about this at all? Not really. I thought this would be more of a topic for you guys, but it turns out it's on the AP Chem test. All right, so that's why I'm telling it to you right now. If I had a guy like nitrogen, which ends, what does nitrogen have to end? Look where he is. His P is going to be like that. Would you expect nitrogen is going to be magnetic? Well, a nitrogen atom would be, right? Because a nitrogen atom, not a nitrogen molecule, would be because of that, because it's got basically 3 unpaired electrons. So you're just looking if they're paired or unpaired. That's all you'll have to do when you're answering those questions. Keep the word di in mind. Di, paired, not attracted to a magnetic field. Di means paired, right? Di means 2, so you think of paired. All right, so that's something I never covered before, but I want you to know for the test. All right, last thing for today then. I said I only have 2 days. I'm going to actually be going over this review stuff from Chem 1, and that's the periodic trends. Let's summarize all the trends that we've heard of so far, okay? All right, and I think we've done this to the point, even throughout this year, I've talked about it enough that you probably know it, okay? Would you all agree that the biggest atoms are down here and the smallest atoms are up here? And I told you way back when I first started teaching this, I can use that to predict the other ones. But I want to make sure you guys can explain this better than what you did back in Chem 1. Think about this. If I asked you why, as I go down a periodic table group, the atoms get bigger, what would you tell me? Why do you think a guy at the bottom down here, a guy like, let's say, rubidium right here, is bigger than a guy like hydrogen up there? What would your answer be for that? Because you guys are still, believe me, after reading your last test from yesterday, lousy at answering those questions. Here's what I hear for bad answers. I don't have time to really get into it because it's a review day. Bad answers would be, well, rubidium's got more electrons than protons, therefore he's going to be bigger. Absolutely wrong. If you say that, you're getting 0 points. Rubidium does have 37 electrons, and hydrogen has 1. He has 1. 37 versus 1. So shouldn't he be bigger? Absolutely not. Coulomb's law. And that's a word you're going to see again. Coulomb's law. I did mention it last year. I gave you a definition of it. I know you don't remember it, but Coulomb's law is very simple. It's not a calculation. It just says that the stronger the positive charge, the closer things are going to get pulled together. That's all you got to know about Coulomb's law. As I go across the periodic table, people, what happens to the size? gets smaller. You know why? Because I have more protons, which has a greater positive charge, a greater nuclear charge. Coulomb's law says that's going to pull closer together. Why, as I go down, do they get bigger? Nope. They're more positive and they're more negative, more pluses and more minuses. You don't remember. You should. Let's draw them out. Here's hydrogen. Here's the next guy down. Here's the next guy down. What do those circles mean, even though they're not really circles? Energy levels. Definition of an energy level is the average distance of the electron from the nucleus. So the reason as you go down a group, atoms get bigger, is you're adding an energy level every time you go down. So you're getting further from the nucleus. If I just fill up the same energy level, like I do in this case, okay, that would be this guy right here. What would he be? Potassium. And I go across, and I take a guy like selenium or bromine on the other side. Here's bromine over here. Bromine is much smaller. He's about half the size of potassium. Why? Because bromine has 35 positive charges inside of him. Potassium only has 19 positive charges. Coulomb's law says he's got a greater nuclear charge. He's got a greater charge difference. They're going to suck themselves closer together. They're going to pull themselves closer together. So he is a smaller atom than he is. If all I'm doing is filling up the same energy level. So that's all I'm doing as I go across. I'm just filling up an energy level. As I go down, I'm adding an energy level. Now, that one trend will predict everything else for you. Would you not predict, if this is the smallest atom and this is the biggest atom, wouldn't you predict it would be easiest to remove an electron from this guy than it would be to remove an electron from that guy? Sure, because here, that positive charge is right next to Coulomb's law. It's held stronger if they're closer together, so it's going to be hard to remove it for that reason alone. But there's another reason too. As I go across the periodic table, I'm getting closer to an octet, aren't I? They're going to want to gain electrons, not lose electrons, right? So for both of the reasons, being the size and the octet rule, I would expect, and that answers all those other questions. Because a nonmetal, it answers that question. What do nonmetals want to do? They want to gain electrons, not lose them. Smallest radius. I already talked about that for the last 5 minutes. Ionization energy. How much energy it takes to remove an electron? It's going to be harder to remove this guy. Electronegativity. What's that mean? The attraction of an atom for shared electrons. They're going to be attracting theirs more over here than these guys are over there. And that's why these are your best metals and these are your best nonmetals. Makes complete sense. Okay. Let's keep going. You may, some questions like that. Could you answer those? We're going to be doing all the multiple choice practice tests starting Monday, right? So, can you answer questions like this? Which one of these guys has 5 valence electrons? What does the word valence electron mean? Outer shell. So who would have 5 valence electrons and the highest energy level is 4? You don't even have to look here. Look at your own periodic table. Who does it have to be? 5 valence electrons means he's in which group? Group 5. 1, 2, 3, 4, 5. So he's one of these guys right here. Okay? He's one of these guys. Now, it says the highest energy level is 4. What does that tell you? What row is he in? 1, 2, 3, 4. He's this row. What element is it? Arsenic. Everybody agree? That would be arsenic. You can write that down in case you don't know. The last orbital to fill would be the 4p3. What would that guy be? 4p3. That's right, arsenic. Yep. It has this electron dot notation, and he's in period 2. What's a period, again? The row. The groups. These are groups, as you all know, and these are periods. He's in period 2, and he's got 2 electrons in his outer shell. That's his electron dot notation. Would you all agree he's that guy? Which is beryllium. Has 6 electrons in the 3d sublevel. Where's the 3d sublevel fill? Look at the periodic table. It's going to be 1, 2, 3, 4, 5, 6. That guy right there, who is iron, you said? That look right? Yep. And has one set of paired electrons in the 2p. Be careful how a lot of these they purposely word things. This is a good one. It's a good type of AP question where you're not reading carefully. It has one set of paired electrons in the 2p. You know what people are going to put there? They're going to put, oh, okay, 2p. What's 2p? 1, 2. Right there, it's that guy. Is that right? No, because he's not paired. They go in one at a time. They go in like this. Then they come back and pair up, right? Oh, I can't do like that one. They go in like this, and then they come back and pair up. So it'll be the guy with 4 electrons or oxygen, correct? All right. Now, sticking with the periodic table trends. Okay? Sticking with the trends of the periodic table. What if they give you, I'll guarantee you, they will give you graphs on this test. We're almost done. Hang on there. Hang in there. Remember, I'm only teaching you for one more day before the AP exam. Over the next 2 weeks, you're going to be doing these tests and practice, and I'll help you with them, and you look at the keys. By the way, when I say the keys, I think you have to understand this. They're not just keys. They're keys where they explain every possible answer. If there's A, B, C, and D, it tells you why A was wrong, why B is right, why C is wrong, and why D is wrong. So it's not like I'll be doing much of anything over the next 2 weeks. You're going to be doing this on your own. So just hang with me for a few minutes. We're almost done. What if they give you graphs? If I give you a graph like that, can you tell me what it is? What trend is that? What trend must that be? We're going to write these down. I want you to be able to tell me, though. Figure it out.
It's just like the cross from that thing.
Yeah, well, notice the thought process has to be, okay, what's this doing across a period? What's this doing down a group? Okay? Well, a lot of people, the first thing people see in a graph like this is they say, oh, it's going down. It's decreasing as it goes. But decreasing which way? Decreasing as you go down a group or decreasing as you go across a period? Across a period, right? Because here's element 2, I'm sorry, here's element 3 to element 10. Elements 3 to 10 are lithium to neon. That's a period 2. So what trend decreases as you go across a period? There's a couple of possibilities. Can it be electronegativity? No, because electronegativity gets better as you go across. Can it be ionization energy? No, because that's how much energy it takes to remove an electron. That gets stronger as you go across. Can it be atomic size? Yes, it absolutely can be atomic size. And that's what he is. This is atomic size. Or atomic, again, radius or atomic size. There's different ways to say that. They probably would use the word radius. Could it be metallic character? Do you have better metals as you go across or worse metals? And this is going down to, now granted, there's no number to metallic character, so it's not going to be that. All right, what about this guy? What's happening across a period for this one? Yeah, this guy's going to be either electronegativity or ionization energy. Now, here's the thing about ionization, how you can tell them apart. Do you guys remember this? Look at that. That also goes across. That also increases as you go across the period, doesn't it? And decreases as you go down a group, which is exactly what you'd expect for electronegativity and ionization energy. But you see these exceptions right here and right here. How do we explain that? Do you remember? Let's see where they're happening. In a periodic table, and I should have a periodic table, that's happening, let me go back here. It's happening between elements 4 and 5 and then 7 and 8. 4 and 5 and 7 and 8, right? Let's go back and I'll show you. Well, we'll use this one, I think. Okay? So it's happening, no, I'll use a bigger one. It's happening between 4 and 5, that's right here. This guy's element 4. Really? Oh, yeah. Let me do play first. It's happening between here, unbelievable, here, and here, right? Let's see if we can figure out why. By all that is good and holy in the universe, it should be harder to remove an electron from this guy. Okay? It should be. It's not. Why? It should be harder because he's got a greater positive charge, Coulomb's law. He's closer to having an octet. Why is it easier to remove this guy? Because here's what this guy looks like. He ends with 2s2. This guy ends with 2s2, 2p1. Hold on before you go. You see what's going on here? What are you removing? an electron, a single electron from a p-shaped orbital, which is not as stable as the s-shaped orbital. And it's only single, it's not paired up, right? So for both of those reasons, it would be easier to remove this guy. And that's why you see those exceptions. It happens again between groups nitrogen and oxygen there. Okay, sorry, you got to go.